Of inertia matrix. As we know that moment of inertia is the rotational analog of mass. Similarly, the angular momentum is the rotational analog of linear momentum. We can relate angular momentum with the matrix of a moment of inertia by the following relation, where omega is the angular velocity of the body with respect to the axis of rotation, and this matrix IP is known as the moment of inertia matrix. Now we'll verify the equation. Consider this body and we have to find the moment of inertia of this body about axis P. Let's consider these are the coordinate axes, and mi be any arbitrary mass on the body at a vector r1 from the origin, and p be at vector rp from the origin. So with respect to p, mi is at ri minus rp. Hence, computing the angular momentum, we'll get the equation summation of I equal to 0 to n, where n is the number of particles in the body, ri minus rp into mi into ri. This is the equation of angular momentum of the body. Now we'll use omega equal to omega 1 I1 plus omega 2 I2 plus omega 3 k cap, and we'll consider that this axis is this point is at origin and the velocity of the point is 0. So the equation will reduce to this: angular momentum equal to summation of mi into r1 into omega into ri. Now we can use vector triple product in this equation. Hence we'll get this form of equation. Now we'll use ri equal to xi in I cap plus yi j cap plus zi k cap. we get this equation by replacing ri with xi plus yi plus zi. Now we get hp equal to this matrix, and we also know that a moment of inertia of a body about x-axis, y-axis and z-axis respectively is given by these equations, and their multiplication is given by these equations. Now on using these equations and putting these values in the matrix, we'll get exactly the same matrix IP that was in the equation that I introduced in the first go, hence thereby proving that relation. Now we'll move on further. Let's say the direction of angular momentum and the angular velocity is same, that is angular momentum is parallel to angular velocity. Then we'll get hp equal to lambda omega, and using the equation that we introduced in the first go, that is hp is equal to ip omega and equating 1 and 2, we will get lambda omega is equal to ip omega. This can be seen as an eigenvalue problem with the three eigenvalues defining the axis about which body can spin, maintaining angular momentum parallel to angular velocity. Now these three eigenvalues are called A, B and C respectively, and the set ABC is called the principal moment of inertia. When the axis of rotation is aligned with principal moment of inertia, IP can be written as